Well, everybody, welcome into this video. I'm delighted to say we're now on the 13th video, lucky 13th video of the series on the NACA 0009 airfoil for use on a front wing in a STEM racing competition car. I'm today in the lovely surroundings of the Southern Regional College in Newry and have got the time set aside just to get this very important video done, which we are now eventually gotten into the mesh independence study after so many promises that the next video would be mesh independence, only to diverge to investigate some other interesting aspect of CFD and the results that we've been getting through here. We have now arrived at one that we will eventually look at it. So in the mesh independence study, I'm going to use the grid convergence index method. Now there's a couple of caveats with this method. This is the method that is preferred, especially for publication standards. There is other ways of doing mesh independence, and amongst them will be looking at a variable of interest and just refining a mesh over and over and over and making sure that the number one, that we are converging towards a certain limiting number or value, and that in every subsequent iteration, every subsequent mesh refinement, the value of that variable is also shrinking. Okay, so that's that you can do that, and then when you effectively see that flat line, you can say, yeah, things have converged. That's fine, but it doesn't really give you the same sort of insight that the grid convergence index method as laid out by PJ Roach does give. So that method not only does tell you a little bit something about convergence, but it also tells you about something about how your model, how the physics and your numerical method that you've chosen, or your discretization scheme, and your even your turbulence models are working. So the grid independence is so much more whenever you use the grid convergence index method. It becomes so much more than just determining a grid refinement level in which the value of this variable of interest becomes independent of further refinements of the grid. Okay, we'll find in this method here typically that if we refine too much, we bring brand new physics into the equation. Right? We bring brand new physics into the flow field, which weren't earlier captured in a coarse mesh, where we just kind of averaged over them, brushed past them because we weren't refined enough to see them. But when we do refine them, we see new things come in, and that is going to have implications to our, number one, to our apparent order, which is really a description of our numerical behavior, but also tell our grid convergence index value. So we could find there that for a particular airfoil at a particular Reynolds number, it behaves very well numerically at a certain grid refinement, but it behaves terribly, from a physics model. It's not indicative of the physics model for the given turbulence model we have chosen, for the given discretization scheme we have chosen. Okay, so it doesn't necessarily reflect that our physics are bad or good. It just says that the mesh and the discretization and the turbulence modeling and our numerical method for solving this physical scenario is good or bad, regardless of what that physical scenario is. If we bring in new physics into it by refining even more, we might have to alter what we do with our mesh to capture that adequately. So that's what the mesh refinement is about, or what mesh independence. It's not just about saying, yes, this is the level of refinement I need. That's it. That is, again, something that you want to find out, but that's only going to work for a certain set of physics, providing there that the physics don't change and that our what's being experienced in one cell is equivalent to what's being experienced in another cell, not with respect to variable values, but the physics of the flow. Okay, so a couple of preconditions on this. So within this here, this uses Richardson extrapolation. Of course, the method is laid out by Roach in 1998, 1997 or 1998. That's it here. That's the paper. Results in this. Oh no, sorry, that's not the one. I'm up here. This is it here. Method for uniform reporting of grid refinement studies, PJ Roach. This was 1994 this was given. I think he explicitly went through a method in 1997 or 1998. But nevertheless, these are the equations that I'm going to be using in the grid convergence index method. This paper here by Selick et al., which is not published anywhere as such, it's available online. If I put a link to that in the comments as well, does give a step-by-step process of running the Richardson extrapolation for the GCSI. However, the equations used in these are slightly different than the equations I've used. So I have stuck with the equations here used in Roach. So I have. And these are the ones we're going to be running with. All right. So I'm going to split this up over 2 videos just to keep it in bite-sized chunks, because in the second video I could see there being less on the calculations of the GCSI and more on the discussion of what the results are, which, yeah, they can be technical. I'll try to keep them as less technical as possible, but definitely I'd like to discuss them in so much as that if you were quizzed by a judge on why if the judge has that much interest in CFD through all the design points and the marked and assessed criteria points of the competition in STEM racing, if they do hone in on CFD and why you've gone for this particular grid or why you chose this grid, at least you'll be able to give some sort of understandable answer or demonstrate a level of understanding for it. So yeah, and I do realize that there's a fine line to walk on this one. So I'll do my best, and we'll see how we go. So the calculation that I'm going to run GCSI in is going to be executed by MATLAB on a MATLAB code. So this is a script that I have written myself. It's very similar to the one that I had written, even though it's more complex. It's very similar to the script or the M file that I had given for calculating out the Y plus value. I tend to do all these in MATLAB. You can calculate grid convergence index in Fluent itself, in the Fluent solver, by creating a new name variable, albeit you will have to create 2 report definitions. You need one for the number of cells, even though the number of cells is reported out of the mesh into the parameter set. Where are we at here? Number of cells mesh here, mesh elements. It is reported there. That cannot be read by Fluent, as far as I know. It can't be read in this system through here. Okay, so what we need to do is we'd need to write another named expression in here or report definition to calculate the number of cells. If we have that, then we'd have all the tools in Fluent to be able to calculate out both P, which is the apparent order, which is the numerical behavior of our mesh, as well as GCSI, the grid convergence index, which gives us kind of a level of confidence that our method, our discretization, is good for the scheme and for the turbulence model and the model we have set up, and it'll give us that to a level of confidence, if you like. We can calculate all that in Fluent, and that's fine. But if we do it in Fluent, it's going to come up here on the parameter set. We can write it out to a report, but there's very little we can do with it after that. So for that reason, what I tend to do is I just take in the extra step of reading it in the parameter set, outputting what I need, and taking the meaningful values out of the parameter set, which will typically be the variables of interest. Kind of the defining variables or parameters from my study, and plugging them into MATLAB and then storing my data in the workspace in MATLAB. Okay, I have an awful lot more, I suppose, opportunity when I write it into MATLAB. So there's a couple of ways we can export it into MATLAB as well. We can right click onto our table and we can export selected design points, obviously a little bit more, into MATLAB, and then run the function in MATLAB and then write that detail out to somewhere else or whatever we want. So MATLAB gives us additional functionality. You do not have to do this in MATLAB. I have always done in MATLAB and I'll continue to do it in MATLAB. Some people do it in Excel, which is perfectly valid as well. It's even arguably a little bit more visually amicable than MATLAB, but I just prefer the workflow of MATLAB. I prefer what we can do with MATLAB and so on, so that's why I'll use that. So if you want to see it done in Excel, let me know and I'll do it in Excel as well. But hopefully you'll be able to take what I've done in MATLAB and extrapolate that to make it fit Excel. Okay, so this is what we're going to do. This is where we finished the last video. We took out our design points that were not required of different angles of attack. What I will say is make sure that the design point that is left is using the angle of attack of 0. That in this current design point here, our angle of attack is 0, all right, because it's an easy one to miss, that you delete out the 0 angle of attack, and the only one that you have left is the 2% angle of attack, or 3 or 4, or one of the other ones. I took out the angle of attack variable out of this, or parameter out of this at the time, so I can't read it here in the design table now, but I am fairly confident that I am running with a 0 angle of attack. If you're anyways unsure, go into your setup or solution and check to make sure angle of attack is set to 0, and you'll find that in your name definition. It should give the value of 0 in that, and that's the one we're going to be using. Okay. So this, I've coarsened my mesh extremely here as well. So I've reduced the number of divisions. So instead of having an awful lot of wee divisions, I have now lesser divisions, which has given me bigger chunks, bigger cell sizes. I'm going to make this here my coarse mesh. Right, this is my coarse mesh. So what I want to do now is create a medium mesh, which is going to be one refinement order greater than the coarse mesh. So I'll take myself back into trusty MATLAB, and this was my coarse was equal to the spacings, which was the spacing I had, the original spacing, right, divided up by R, which is my refinement factor raised to power 3. So I reduced this by 3 orders. So what I'm going to do is start with coarse being mesh 1, so, or mesh 3. I'm going to call this here, let's say 3 is mesh 3. I'll tell you what I'll do. I'm going to call this, I just leave it as coarse. And I'll go for medium now. Medium is equal to coarse. Right. So what I want to do with this one here is I want to refine this. So I have split up my mesh, and when I mesh this by spacings on my boundaries, right, as opposed to cell size. So what I want now, if I increase the amount of spacings, I increase the amount of cells, and for a given distance, by increasing the amount of spacings on it there, my cell size have got to get smaller, right? So what I'm going to be doing is I'm going to multiply this by R. Now, if you're in your discretization procedure, if you have done it in accordance to cell size, what you're going to be doing here is you're going to be doing everything opposite that I've been doing. If it has been a cell size, right, and I started with a very small cell, and I wanted to very much so coarsen it first, I would have multiplied by R to the power 3. And similarly, when I'm at the very coarse, which is my starting point, that's square 1 at the coarse, if I was using if I was defining my mesh size and my cell sizing by cell size, right, in the discretization space, I would be dividing by R. Okay, so I would be making my meshes smaller, my grids smaller. But me, the way I set this up was by the number of divisions on the boundary. So to make my cells smaller, I have to increase the number of divisions. So that's why I'm multiplying by R here. All right, medium is going to be coarse by R. I'm going to let that output to there, and then finally fine will be equal to medium by coarse by R squared, or medium itself by R. So I went from coarse, right, multiply that by R to get medium, multiply that by R again to get fine. All right, let's F5 that, and there's my grid spacings here for my 3 meshes. All right, so I already have 78, 42, 42, and 64 in Fluent. Let's see here. 78, 40, 42, 42, and 68. So in this design point, I'm going to put in my next one. That kind of backfired on me here. All right. I have a 110, 60, 60, and 90. 110, tab, 60, tab, 60, tab, 90. And then, of course, for my fine mesh, I'm going to put in a new one. which is down here. I'm going to start with 156. Again, rounding to the nearest integer. Can't have fractions of cells. 85. Oop, put it back over here. 85. The next one should be 85 as well. And then the next one should be just over 100. 127. 127. Grand. Bring that down, bring that up. So there's 3 mesh sizes, from coarse at the top through medium to fine, up by the number of divisions. So what I'm going to do now is I'm going to calculate these design points and calculate all my new parameters for each one. So update all design points, right? What actually I'm going to make I'm going to retain the data from each of these. Not that I'm going to do much with it just for now, but I'm going to retain it just for now to see what we get out of this. Update all design points. So this is start to execute, and you should see fairly quickly this first one resolving, design point 0 resolving, because we don't have that many mesh elements to run calculations in. But because we're using a refinement factor of √2, we're doubling our mesh sizes here on a 2D evaluation or 2D analysis, and we will then be able to see that this is going to get progressively longer to calculate. What do we have here? Design point 0, update a solution component fluent for design point update failed. I'll tell you why that probably is. I'll move my mug over to here. I'm just going to stop that, and I'm going to abort that altogether. If I go back into my project, when I took away my variables and whatnot, I probably should have updated my project. If you see that, it will keep executing, it'll keep running, but you can't be obviously confident with the values that you're going to get out of it. So I'm going to run back into project, and we could see something not great happening here. Let me just give a refresh on the project. Updating on the project is not really going to do anything, because we're going to have to run through these calculations here again. It probably did resolve itself when it failed that first time, but maybe it was a case that it just couldn't do 2 things at once. So what I'm going to do is I'm going to try to run it here again, and see what we get happening. All right, when this is being set up, what I'm going to do just to save time, I was going to pause this and just let it run through. But what I'll do is I'll go back into MATLAB and I'll bring in the function. Then I'm going to use my GCSI function, and I'll explain that, and then we'll pop back into here, see what it looks like, and if it's still taking a long time, I'll then use it to pause it if I run out of things to do when I'm waiting. So in the MATLAB, here we go. Let's bring down the size of that screen there again. I'm going to scoot myself in a new project, new script here, and what I'm going to run is this GCSI. You see it over here in my files, so my active directory. These are my kind of function files that I'm just using for these videos. The GCSI roach. So I have underscore roach in that because I have another GCSI file which I don't use roach's own equations, but this one here I'm going to use roach's equations, and we'll see how that goes. So again, anytime you have a function or you have it in there, you're not that sure how to use it, we're going to be looking for certain inputs to put into this. What inputs do I need to put in? If I just drag this in, which I will do, and drop it, okay, this will open up the function. So you can see there's an awful lot in it. There's a few checks in it. I've given it as much description as I can here on the top bit. So the reason there that there does be percentage signs where there's no lines is that if I left a space off there and I typed it into help, and I pulled up the help pulls up what gets written until it sees a space, and then it stops executing. Okay, so you can drag and drop it in there, but you're not going to execute your function there. So what I tend to do is I come into help and then space, and then I put my function name in. It will prompt you to a script that it sees in the active directory, of course. So help GCSI results, I'll hit enter, And then in here, as you see, it gives me a good description, because that was all my commented stuff at the top of that script. So we could see here, this is my function. Results, GCSI function. And by the way, I wrote this as a live function as opposed to an M file, so it is an MLX file. Let me just see V and put that into there. Actually, what I'm going to do in here, Control Alt Enter for a new space. Live editor. I'm going to scoot myself back in here. Space up and text. And I call this execute. Execute GCI. And up here, I'll give myself a wee bit of text and say enter parameters and variables. So as far as ANSYS is called, whether it's a variable or parameter, just referring to it as parameter. So I normally wouldn't use them interchangeably, but in this case, if I say a variable, I mean a parameter. And if I call a variable a parameter, I've done it just to generalize everything. Okay, so for the purists there, I take your point. Okay, so enter the parameters of variables. So what do we need to know here? So here we are, R, H3, H2, H1, phi3, phi2, phi1, N3, N2, N1, and D. All right, so what I'm going to do here is I'm going to put in a note, actually write that in the script under a comment maybe, and say that course mesh is represented by postscript, it's not a subscript in this case, by postscript 3. Alright, let's get an inverted comma on that. Oh. Right, so anything with a 3. So N3 is the course mesh. N is my number of cells. Phi is my variable of interest, and H is my characteristic cell size. Our medium mesh is represented by postscript of 2, and the fine mesh is represented by postscript of 1. All right, so I'm not going to bother writing in what R, H3, and N is. Okay, we're just going to run with them. Execute GCSI. I'm going to say for phi equal to, let's go for drag coefficient. So drag coefficient will likely be the variable slash parameter that behaves best with this method. So we need to make sure that we have asymptotic convergence on this, which means there that we're converging towards a value which will be an extrapolated theoretical value if we had an infinite amount of cells, or an infinitely small cell size, or infinitely large amount of cell divisions, or boundary divisions. We need to be convergent towards that value, right? So that's a precondition around this. That is a must. We also must make sure that from mesh to mesh, from refinement to refinement, that our difference in our variable of interest, in this case drag coefficient, gets smaller and smaller and smaller. Drag will be good because it is dominated really by skin friction on the airfoil surface. So the skin friction, very momentum based, which is great. It will behave very well, where drag and lift will behave for our mesh up till a certain state, I think. So remember when we brought in the angle of attack onto that, the angle of attack worked well until it hit a certain value, the angle of attack, and we said that was really because it converged at a snapshot in time. I was probably a little bit maybe misleading when I mean a snapshot in time. Obviously on a steady state analysis, you get a calculation of pressure and velocity at each grid centroid, at the middle of each grid, and then it's averaged from, we start with an initialization and obviously a very bad estimation of what they are till we get to the final one. But the final one there is based on our calculations being completed. Let's bring that down. Our calculations being completed at a certain time. That's what I really meant by that. But it isn't averaged. Right? It's not time averaged. It's spatially averaged only. There's no time dimension in it. Right? It's spatially averaged at this flash in time. That's what I meant when I meant snapshot. Not that it just picks a value and says, yeah, you look good here. It means at this snapshot in time, time doesn't change. This is the average spatial results. What happened then was when we changed, I think the pitch on that, at that one grid refinement, it wasn't able. New physics were brought in, which introduced an instability. So I think it was more of a physical breakdown, more so than a discretization breakdown, which we could calculate. We could calculate better at that angle of attack, possibly using a different turbulence model, or maybe using a different discretization scheme, or a different resolution of our mesh. All right, so it doesn't mean there it's always going to fail an angle attack of 5 or 6. What it means there is that most likely that our mesh, our discretization, our modeling hasn't been able to calculate that adequately. And one of the ways out of that was obviously to move into evaluate not only as a spatial analysis, but also as a temporal analysis by using a transient analysis on that. Okay, so the mesh independence is going to do something very similar here, except what it's going to do is going to find at what resolution are we able to solve the physics of this flow best. If we get too fine of a mesh, what's going to happen is we're going to start resolving things that we previously didn't resolve, and we'll find there that either our turbulence model or our temporal model or our discretization model, usually with the discretization model, isn't capable. It's not good enough for it. We need to change something. So that's what the grid independence is. And that's what we're going to try to get a capture on here. So I don't want to go into too much description now without having numbers to back it up or to explain. And again, I try to reserve them for the second video. But anyway, we need to put in values here, interparameters values. We need to put in an R, a H3, H2, H1, and so on and so forth. Right? So I'm going to go for R. We know this one here is going to be root 2. Right? So it's 2 raised to the power of 1/2. Right, or SQRT, open bracket 2, close bracket. Right, don't need to report that. So that's what R is going to be equal to. Next, H3, H2, and H1. Right. So what I'm going to do here is maybe split these up and say put in coarse grid parameters, medium grid parameters, and of course fine grid parameters. So split this up as you want. I like commenting. Mightn't seem that way when you look at the functions that I write. Sometimes I just get rushed through them. But again, that GCSI wrote function, I'll put that into the comments. Feel free to use it. Coarse grid parameters. So for my coarse grid parameters, these are all my 3's. All right. So I'm going to have a H3 is equal to something. I have my phi 3 is equal to something, and n3 is equal to something. I put n up here. Why? Because it's the first one that comes out of my table, I know. Control C, Control V, n2, h2, and phi 2. So yeah, maybe you prefer to organize these as n's together, h's together, and phi's together. Right. Different horses, different courses. I prefer it this way. Oh. And then of course I have another parameter left in here to enter in D, which is the dimension. Right? So this is a two-dimensional one. So this is spatial dimension as opposed to kind of physical dimensions. D is equal to 2. Right, so I'll just tell that just in case that's not obvious. This is 2D as opposed to 3D. Nice, so I should be able to get some values for this now. So I'm going to minimize kind of reporting pane, bring that in and bring in this and see what values we have in here, what we can take. So yeah, look, it's all calculated actually, so it didn't take all that long, which is great. Right, let's get some values entered in. So by the way, so see when I have the three of them here, just for the sake of going a step, if you right click that, all right, and say if I take all three of them design points, right click, I can export the selected design points. So if I had a massive table of design points here, this is something that I might, an option that I might use. Oh, let me just say, duplicate export. No, there, export the table as a CSV. Usually this will be overwritten. All right, let me just do it as a CSV. Export table as a CSV. We can stick that in somewhere. I'll just put that just for now into downloads. So again, I'm kind of diverging a wee bit from here. Let me see data. It's called data. So what you can do there now, if you wanted to automate this slightly, and again, if I had more design points and I didn't want to keep having to write these all in, what I would generally do now is go into home, I'd import data, I'd go then into my downloads, there's my data file. This will open up a new window and it'll ask me which columns I want to bring in, and then I'd write a script then tell say which columns that I want to bring in for there. Variable 2, variable 3. It's not actually just set up the way I'd want it. Delimited fixed width. Yeah, I'd probably set that up slightly different. Let me just see what we have. But it's brought in the table there. Close CSV. Yeah, don't want that. There we are, there data. So I could read into that data and pull out the respective columns that I want. So there will be a wee bit of setting up to do on that first in the CSV before you bring it into MATLAB, just to tidy it. So you'd want to be able to delimit them columns to organize the data in the columns you want. But that's generally what I would do. And then N3 will be equal to data and the reference in the data. Okay, but nevertheless, we only have 3 to deal with at any one time in this method. So we're just going to do it manually. And let me see, so I have DP0, right, so we're going to do all our DP0s first, which is our coarse mesh. So let's see what we're looking at. What do we have? So our mesh elements, so N is equal to 22032, bang. Next thing I'm looking for is my characteristic cell size, which is, where's characteristic cell size? I hope I left that in. Mesh divisions, mesh min, mesh inlet, mesh elements, y plus lift coefficient. Oh, there it is there. Apologies, that was a wee bit down the road. 520025 is my characteristic cell size in that, and then my phi value, I'm looking in this one here. What did we say this one was for? We are going to be looking at drag coefficient in this one, just by choice. Well, there's drag coefficient right next to it. So for my coarse mesh, my drag coefficient is 0.0159442. 0.0159442. Just when I'm here, I'm going to do phi 2, which is my medium design point 1 here, is my medium grid. I'm going to come all the way back to where I had it here, because I'm local to it, 0.0158877. My phi value is, oh, did I get that one wrong? I did. Apologies. That 158 is my drag coefficient actually, sorry. The drag coefficient. H2, that'll be a big cell. My characteristic cell size for this one is 0.0037938. How many significant digits do you put in? It's up to yourself. I'm going to just write in what ANSYS has given me back. Yes, I can write into 3 here, but I'm not. I'm going to try to stay disciplined and do this on a refinement to refinement basis. And our mesh elements for this one is 41,000. Oh, don't put a comma in there. 400. So we had a big rounding factor there in our refinements for our cell spacing. So we're not quite at double. but we had less of a refinement, you know, a rounding, if you like, between medium and fine. That's why for our next one, for our fine grid, between our medium grid and our fine grid number of elements, we are just simply doubling. So I'm going to go now into my fine grid. Mesh elements n is 82,804, semicolon, one down a line. And now I'm looking for my characteristic size, which is here. Characteristic size here is down to 2 mil, 0.0026825. That's 5. Jeez, that's the second time I've done that. Put it into the wrong one. Against the order in which they're coming up here. Normally, I probably would have calculated that one first, but there you are. You can never be too careful. Phi 1 is going to be my fine grid for my variable of interest, which we're still looking at drag coefficient, obviously, 0.0158618, and semicolon on. Now, I'm going to shoot down answers, and there we are. So there's everything I need to put in for this. I'm going to execute this this function, and let's go. Let's see what we got. All right, so I'm going to F5 that, bang, F5, and there we are over here, our output tables. I should actually change the color of that line. This is about the 12th time I've said that, and I've never done it, but I do promise I'll change the color of that line in the function. Calculation plots are down the bottom usually. Plots, plot arrange. Okay. I don't know. I'll just take out the key on that there. Just give a different thing. It might default there to blue or something. Plots. All right. And we'll see you on the next one. So yeah, so here's my analysis. So I'm going to stop the video here, and I think we're going to go into the analysis on what these numbers mean. It is important that we do know what the numbers mean, and it's important to know, yeah, are we done? Or are we not done? And have we look at what's going on. And by the way, we've only done this with one variable. I'd like to ideally do this with another two, even though I wouldn't be as confident of the consistency with the other two. So yeah, there is just under 38 minutes. I'm going to stop the video, we'll upload this one, and then when we come back, in the next video, we should be looking at this screen. So thanks very much for your time. Thank you.